Hey, hello, biology students. Hey, welcome. Hey, thank you for playing this video. Actually, I joked with the A&P people, especially at Crowder. I mean, they're the ones. Those are the ones kind of they're the front runners. I mean, their videos come faster than everybody else's videos, or I should say, they. I don't know how I want to say it, but anyway, they see them quicker. Earlier, I guess, I don't know. I just botched that. But anyway, that was not a strong teacher move right there. So, but I was just joking with them that we have renamed these. They're no longer considered video lecture series. They're now podcasts. And there's a reason why. It's kind of humorous. But it's more, this is not so much a video of you watching me lecture over the material. It's more of a video of you watching me tell you about it. And at times like this, you know, the head can be down, looking at notes. I could be typing. So we're starting to call it now more of a podcast. Because like if you watch ESPN or just a podcast of people doing stuff, it's more like you're just watching them do it and the camera just happens to be there. And that's kind of more what this is. So, and plus that may even make me seem more cooler than a lecture series, which would be very, very academic, which that is not my style at all. So maybe I am more of a podcaster, a biology podcaster. Maybe I should get into that business. I don't know. I wonder if that would move the. See, what are the kids calling them? Social media. Is it movers? I don't know. Social media something or other, you know. I guess that's how uncool I am. I don't even know what the phrase is. So, on that uncool note, hey, again, welcome. Hey, thank you for opening this up. Appreciate you guys. Love you guys. And thank you for doing this. Love being a part of your educational journey and everything. Hey, we got some cool stuff. And plus, we got some, let me back up. We got some cool stuff to talk about. The things that we're going to talk about today, I do have. Oh, I got my pens already up here. What do I got? Oh, nothing selected. So let's go. Let's go red here. Nice little teacher red. This stuff right here, and not so much this, but you can kind of see it down here in the corner. A little ATP. Those two things that we're going to talk about today, man, we are going to talk about them a bunch. Okay, if you're a high school student and we do 6, 7, and 8. Man, you're going to hear those words so often, and so many times you'll be hearing me say, now, what was that called? What is that called? Because when it comes to oxidation reduction, when it comes to ATP processes, I mean, what the cell does to generate energy is phenomenal. See, it was in switching classes. To the bio Crowder people 102, Jerry and Austin and I it's going to be a while before you see it, before these guys see this, but the last time we were together last Thursday, we talked a lot about just how phenomenal the cell is, and it was part of our plasma membrane discussion, but just phenomenal what it does and how it generates energy, and it's what we're going to be talking about in this case, but it's absolutely phenomenal. And if you're in the A&P class, you're also what? Oh, you know what? I didn't think about that. No, wait, let me think. Energy. No, they split off. They split off after 4, or after. They're split off. So scratch that. No A&P people. They can't ask Trayton Rainey how much time we hear. But if you know Trayton Rainey, see him in the hallway, you can ask him how many times we're going to talk about oxidation reduction, ATP. And his eyes will just roll in the back of his head and say, oh, brother, too many, too much. So we'll see about that. So if you know him, ask him and just see how we'll have some fun with that. But, hey, again, thank you. So let's get started. Mainly I want to get started because you can't get finished until you get started. Is because, man, we're doing something pretty big here at the house. We're making some homemade pizza tonight. We got some Italian sausage smoking in the smoker. And cooking up. We've got some pepperonis that were also in there getting ready to go. And as soon as I get down here, we're going to make us some crust, nice cornmeal, If you know anything about, if you travel around, you've been around, let's say like you go to Columbia, you ever been to Shakespeare's Pizza? They make a nice cornmeal crust. That's the kind of crust we're making. And it's kind of, you'll also see it in a lot of restaurants that do the Chicago style, like the Chicago pizza. It used to be one in Springfield. Man, it was fantastic. That's where we first fell in love with cornmeal pizza crust. But anyway, if you want to see me after you watch this, let me know, or let me ask me, and I'll tell you all about it and how great it was, because it's great every time. I make a pretty mean Italian sausage and stuff those pepperonis, make our own little grinder and stuff. But let me quit talking about that to make myself hungry even more than I already am. So here we go. Let's get started again. Thank you for being here. Let's jump in and talk about these things. This won't be a tremendously long one. Yay, both me and you, but incredibly important. All right, let's get these arrows out of the way because I'm going to need that room to talk. And this is the second video of the day. The first one was A&P, and this is a new feature that I guess over the week, my whiteboard, Microsoft whiteboard, you can see here, updated a little bit, and I got that cool thing there. I don't know if I like it or not, but you know, I can find everything. And let's see. So yeah, we're going to start with a pen, but then we'll type a little bit. Now, if you're a high school student, and when we're checking notes, man, we're going to want this diagram. We're going to want this diagram, and then the ATP diagram. So you will need to draw those three diagrams. When I check notes, that's what we'll be looking at. And if you don't have those, I'm going to be saying, what's going on? What are you talking about? Frowny face, all that stuff. And then you can come back and take. So just do it right the first time. Grab them along with the things I type here, and then down here for the ATP. All right, so let's talk this diagram right here, because this is super, super, super important. If you don't take the time to truly understand a redox reaction, an oxidation reduction, then you're going to struggle when we get to 7 and 8, because I'm going to be saying it and saying it and saying it. We're going to be showing it. We're going to be pointing to it when it's happening. Because when we do the Calvin cycle, when we do the Krebs cycle, it happens over and over and over and over again. And if you don't have in your mind, okay, what those are, no, hang on one second. Sorry about that. That was not a strong teacher move. I started getting a little cool, so I took a glance and the fan was on, and so I went and turned that off. So here we're back. So if you don't understand those two words and what's happening with the electrons, then you're going to struggle when it comes time to understanding it and explaining it, because that's going to be certainly a prompt will be to explain what a redox reaction is. And if you don't include all the parts, I mean, you just won't get all the points. So jump in, mentally wrap your head around what's going on, and let's knock these things out. So you can see from this diagram, when a molecule, I'll type it, but let me just say it all first, and then we'll type it up so you can be sure to write it down in your notes. Okay, when a molecule, all right, when molecules, these two things happen in tandem. So one molecule will be oxidized, and you can see here that's a loss. That's a symbol for electron. Loses an electron, and another molecule is reduced, okay, or has a reduction. Reduction means it gains an electron. And right away, and I will type this over here, but right away you're thinking, how can it be a reduction if they gain an electron? Okay, it's an electrical status. It's a numerical reduction, because we're adding a negative force. We're lowering the energy level. So if a molecule is at, we'll say, if it's being reduced, if it's an electron carrier, maybe it's a +1 and it gains an electron, so now it's neutral, okay, or a 0. So we're reducing the numerical. So the reduction is the energy level, okay. The charge level is probably a better way of saying it. Matter of fact, that is the right way of saying it. It's reducing the charge level, and that's how I'll type it up here. So when we oxidize, it loses an electron. So the big picture of what's happening here, and when we get to cellular respiration, which is the next chapter, you'll see it. It's the glucose molecule will be losing electrons. The glucose molecule will be losing electrons, and the electron carriers, the NADs, the FADs, which you know nothing about right now, but you will know plenty about them by the time chapter 7 is done. Those electron carriers gain the electron. So the glucose molecule is being oxidized. The electron carriers are being reduced. In other words, their charge status. And maybe they're a -1 already because they've already taken on some electrons. But when they take on another one, now it goes from -1 to -2. Okay, so we're reducing. So if you think of a number line, if I go from -1 to -2, that's a lowering, okay, of the charge level, and therefore considered a reduction. So, and that's the idea of what's going on with a big picture example of what's going on. So let's close this. Let's get to typing. Oh, I got to do it up here. Yeah, there it is right there. So get me a little box here. And I'm going to put it right below. And I'll just number it 1. It's a way to signify that we're about to make a list here. Now, a redox reaction, simply it's a amalgamation of the two names. Just simply like you would do, like they do with Hollywood couples. They take part of the letters, part of the word, or part of the name of one, and part of the name of the other, and kind of put them together to make a name. Like if you're a Big Bang Theory fan, like I am, when Sheldon and Amy got together, Penny called him Shamey. Actually, I think it was Leonard, but anyway, it doesn't matter who it was. Call him Shamey. The S-H for Sheldon, and then the Amy, put those together to get a Shamey. So you see the R-E, and then the ox, or R-E-D, I should say, and then the ox. That's a redox reaction, and these things go back and forth. Okay, so let's start making our big picture list. So we'll do ox, and that's short for oxidation, loses electrons, and that's gonna be like glucose when we get there. 2, the reduction gains electrons. So 3 is going to be, the reduction is lowering of the charge. 4, these happen in tandem. Now you can also think like an ionic bond. Okay, ionic bond was kind of the same concept, to where a cation lost an electron and an anion gained an electron, and it happened simultaneously. Okay, an ionic bond, the electron moves from one element to another. Same thing happening here, except this time it's molecules. So a redox reaction is similar to an ionic bond, in which the electron is transferred from one molecule to another molecule. And so I'll put 5, think ionic bonds. And when we are in class, either class, whichever you are, Crowder, we'll do it obviously the one night that we're talking about, chapter 6 here, which will be 2 weeks from this past Thursday, because you have a test coming up. Spoiler alert, which already happened by now. Think ionic bonds. But we're in the classroom at the high school. We're going to do these a bunch, because we'll be studying it roughly a month, and so we will do these redox reactions over and over again with our chemical building block modules, killing building block sets. So think ionic bonds. It's electrons because that's where the energy is. Okay, and you'll see that once we get to the end of chapter 7. So that's redox reaction. But again, you gotta wrap around your head that if we say something is oxidized, it's losing an electron, or an oxidation has occurred. Something has lost an electron. A reduction gains an electron, and those happen in tandem, just like an ionic bond. And the reduction word refers to a lowering of the charge. All right, now, when we think these redox reactions, one of the things that we want to think about is the law of thermodynamics. And we won't spend a lot of time here, nor will this be a test material, but I do want to see the diagram, because here's what we're talking about. When we're talking about energy, we're talking about, excuse me for a second, getting a little dry. We are talking about order and disorder. Now, if you can imagine, pretend this is an ice cube. Okay, if this is an ice cube, that's the simplest explanation. If we took an ice cube and just set it on the counter, just walked away, okay, nothing was going to be done to the ice cube except just setting it in what we call room temperature air. Over time, what's going to happen? Yeah, the ice cube will warm up, okay, and the water molecules will get more freedom, and eventually, if you wait long enough, there'll just be a big puddle of water on your countertop. And that's going from a very ordered environment to a very disordered environment. And disorder in the energy world happens spontaneously, just happens naturally. Things go from ordered to disordered naturally, okay? And that's because energy is being introduced into the environment at all times. In this case, the energy is the heat, the warmth of the room, and that happens spontaneously. You don't have to have any energy for that to happen. Now, organization, as you can see here, requires energy. If I want that water to go back into an ice cube, that's going to take some energy. If I put it into an ice cube tray, that's fine. But I could just wipe it into a cup or anything, or I could just refrigerate that area. But anyway, to get the water molecules back into a frozen state, that's going to take energy, whether it's from refrigerator or whatever. That requires energy. So that's the law of thermodynamics. It applies to what we're going to be talking about today. So the ink tray is closed. Let me go up here. Oh, I didn't mean to grab that. Let's come over here and move this. Center that up here, and I'll just type below. But the first diagram, so let's get a pen here. Now we're going to talk ATP. Okay, we're going to talk ATP, and we will be talking ATP if you're a high school student for 3 months, because it's here in 6, it's in 7, it's in 8, and it's incredibly important to everything that your cell does. We've already seen this reference to ATP when we talk plasma membrane, because ATP was required for active transport. Okay, to get those ions, to get that electrochemical gradient set up, to get those ions to move across, which generated primary active transport, and that allowed secondary to occur, because the amount of energy that you use is more than is needed, and therefore instead of wasting it, we coupled the transportation of glucose through there. So, but let's talk structure first, and then I'm going to use this diagram to highlight where this energy is coming from. But we're going to So we're going to talk here first. And that wasn't a great arrow because I'm not actually pointing at it. But ATP has three parts. Okay, the first part we're going to talk about is a nitrogen base. Okay, a nitrogen base, and that's adenine. And that's what the A stands for, adenine. You saw this in DNA talk. It's the A for DNA. When A and T are put together, that's the A. So that's adenine. So you can see it'll always be this structure right here, adenine. The second part is this sugar, okay, ribose. So that's the second component of ATP, and ribose is not within the letters, and the TP is a reference to the third part, and that's these three phosphates. Okay, phosphate group 1, phosphate group 2, and phosphate group 3, triphosphate. So ATP, adenine triphosphate. Of course, if we were truly naming it, properly naming it, we'd say it'd be ARTP, but you know, I didn't get a voice in that decision because people forget about the ribose because it's not in the name. But that's the three parts. So let's close this. Okay, let's get this little box here. And we'll put ATP. Okay, and then we'll put three components. Okay, 1, adenine. Okay, that's the A. So I'll put that, that's the A of ATP. 2 is ribose. Okay, that's the sugar. That's the sugar that we see right here. And in 3, oops, forgot my dot there. 3 phosphates, and that is the TP of ATP. So 3 phosphates. All right. So I'm actually going to take this and move it over here to get more room to talk about this. So I'm going to slide this down just a little bit. Get my pen here. So we'll talk first, and then we'll type second, so you can kind of hear everything, and then we'll take the notes over it. So this is that cycle that we mentioned way back at the beginning of video 1. Oh, didn't mean to do that. This cycle right here, photosynthesis, cellular respiration. We talked about it being a cycle. And there's our oxidation reduction right there. We talked about being a cycle, and that is highlighted by this diagram that we're going to look at now. I'll put that arrow right there so it's pointing at me. Well, that wasn't what I wanted. So we'll try this again. It'll be a lot bigger though. There we go. And now I'll put the arrow back there. Alright. So ATP cycle. So I've got cellular respiration. Get my pen here. I've got cellular respiration, and I got photosynthesis. Now, we haven't got to either one of these chapters yet, okay? Well, we soon will, but hopefully you know that photosynthesis is the process of plants making the sugar molecules. And cellular respiration is the process of animal cells breaking down the sugars to get energy. And this is done by removing, and I'm going to go a different color here because it's all that red, by removing that third phosphate. Okay, that third phosphate is removed. And how our molecules removed, or how our molecules broken apart. Dramatic pause here. Hopefully hands are going up everywhere. People are screaming at the screen. Hydrolysis. Okay, hydrolysis is the process that in which molecules are broken down. Remember the OH, if you see this, get this O here, it's connecting those two. Remember our bonding element is oxygen in a lot of cases. and that the water molecule, little H2O, water molecule would have came in, and one H attached here, the other OH on the other side, and then we've got those OH bonding sites replaced. And hydrolysis is the answer. So, but when that phosphate is broken off, energy is released. Okay, energy is released, and that's the energy that we're talking about right here. Okay, energy is released. Okay, it's broken apart, energy is released, and that energy is used then to put that glucose molecule, the next glucose molecule, together. So in other words, and you'll hear this metaphor a bunch of times, so I'm just going to put it up here. When you think of your cell breaking apart ATP for energy, think about a machine. Okay, you got a machine, and in that machine you can put $1. And then you get out of the machine $5. Okay, $5. That's what your cells do all day long. And you'll hear this metaphor example 1,000 times because it's a good indication of what's happening within your cells. Because the energy that's required to put the sugar molecule together, glucose molecules together, is small, but the return when the molecule is broken apart, energy released, is big. So if you can imagine a machine where you put $1, and the $1 refers to the building of the glucose molecule, then you get 5 back, and that refers to the cellular respiration, breaking it apart, and the energy being released. You can also think firecracker. It takes a little bit of energy to take that gunpowder and put it inside the paper and fold it and prepare it just right. But when you light that firecracker and throw it on the ground, the energy released from that, okay, is a huge amount. Okay, huge amount. So a little bit of energy to put it together, big energy when it's released. All right, and so that's a process that we're going to talk about in 6 and 7 and 8 a bunch of times. So, but that's the idea. And of course, this is, if you think about it, when this breaks apart, I mean, that's, again, just a huge amount of energy. And again, we'll talk about this a bunch in class. We'll build this. Doubt that the Crowder students will be too interested, but in the high school setting, we'll certainly build this and break that apart, put it together, break it apart, put it together, and release that energy. But think about that 1 to 5 metaphor here. That's what's happening. But again, you'll hear that a bunch. Let me see, what else do I want to say about this introduction to the ATP cycle? No, I think once you get this diagram down and you get this diagram down and the stuff up there, I think that's going to be plenty. So I think we are going to wrap this one up. Again, I promised you it wasn't too long, but it was just too much to add to the previous energy stuff. It made it too long. So, hey, take care of this information because this is super important information. The ATP cycle, the oxidation reduction stuff. I mean, those are test prompt questions, and they'll be part of the multiple choice questions as well. So take care of that information. But more importantly, take care of yourself, take care of your family. I hope everything is going well with everybody everywhere, with all the craziness going on and the uncertainties day to day. Again, appreciate you guys watching this. Love you guys. And with that, until next time, hey, we will say goodbye.